Hello everyone, let's analyze. So today we're going to talk about the idea of continuity, which, as you might imagine, is a pretty important idea. In fact, it's so important it's likely that you've already heard of this word, and you probably have an idea of what it means. You probably had it defined in calculus. You probably even had it defined at some point in high school. A common rule of thumb definition given in high school is that a function is continuous if you can draw it with a pencil without picking up your pencil. Well, the reason that rule of thumb is given is if f is defined on a continuum, the real line or an interval, then a small change in x ought to result in a relatively small change in f. And that relative small change should be somehow connected. So let's give a rigorous definition. Let f map a subset of the real line to the reals. Then we say the function is continuous at a point x naught if and only if for every epsilon greater than 0 there is a real delta for which the following statement is true. If x is in the domain and the difference between x and x naught is less than delta, then the difference between f of x and f of x naught, of course an absolute value, is less than epsilon. So as we read through that, you might think to yourself, well, that sounds a whole lot like the definition of a limit. And in fact, it is very similar. You might even think that this looks exactly like it with the replacement of L, the limit, by f of x naught. But there are some differences between the definition of continuity and the definition of a limit. So let's talk about the differences. One is that x naught is not required to be in the domain. One is that x naught is not required to be an accumulation point of D. The other difference is that the difference between x and x naught is not required to be greater than 0. It, of course, could be equal to 0. But that case is really a rather trivial case, because if x is x naught, then of course x minus x naught is 0, which is of course less than any arbitrary positive delta. And if x equals x naught, f of x minus f of x naught is also 0, which is of course less than any positive epsilon. The other difference is that we didn't need previously that where we compute a limit x naught needed to be in the domain. But for the sake of continuity, we do demand that the function is well defined at x naught. In other words, we demand that x naught be in the domain. But of course, it is related. So let's talk about how it is related. So let's consider these 3 points. One is, and as we mentioned, f of x naught must exist. Now, if x naught is not an accumulation point, then really that's all that's required, is the existence of f of x naught if x naught is not an accumulation point. Now, could you prove that? That, of course, actually breaks the definition of drawing a function for which you don't have to pick up a pencil, because if x naught is not an accumulation point, then you're no longer defined on a continuum. Now, if x naught is an accumulation point, then in order for f to be continuous at f of x naught, the limit as x approaches x naught of f must exist. Furthermore, that limit must be equal to f of x naught. So if x naught is an accumulation point, then it essentially becomes like the definition of a limit, where L is replaced by the evaluation of f at that point. But if x naught is not an accumulation point, all you need is that f of x naught exists. You ought to be able to prove that, by the way. So let's go over a few examples. Let's consider the function defined on the open interval 0 to 1. And the function is the identity function, f of x equals x. Now, that function is not continuous at 0 because, well, 0 is not in the domain. Well, let's take a look at another function, g of x equals 1 over x. It's also not continuous at x not equals 0 because, again, 0 is not in the domain. In fact, right, 1 over 0 is not defined, which means it cannot be in the domain. So, if we were to go through our checklist, right, we can think of 1, 2, and 3 as a checklist to know when a function is continuous. Right, again, the checklist is the checklist of 1 if x naught is not an accumulation point. But 0 is an accumulation point of the open interval 0 to 1. So we really need to go down 1, 2, and 3. All right. So here, condition 1 is not satisfied. Because f of 0 is not defined, f of 0 cannot equal the limit as x approaches 0 of f of x because this right-hand side is not a number. This exists, but of course it's not really relevant because it can't equal f of 0 because there is no f of 0. Now let's take a look at an example that we've seen before, the function sine of 1 over x. The function sine of 1 over x is not continuous at x equals 0 because the limit as x approaches 0 of sine of 1 over x doesn't exist. So if the limit as x approaches 0 doesn't exist, then the limit as x approaches 0 of f can't equal f of 0. Of course, f of 0 also doesn't exist, so they doubly cannot be equal. But even if I were to define a function piecewise, let's say f of x equals sine of 1 over x if x is non-zero, and f of x equals 0 if x equals 0. Then this right hand would be defined, but this still would not be defined. Now, let's also consider the function p of x equals x everywhere except for x equals 0. So if we were to imagine drawing p of x with our proverbial pencil or pen, it'd be the line that starts in the third quadrant, goes up at a 45. However, once I got to 0, I would have to pick up my pencil, move down by 1 unit, draw a point, go back to where I left off, again by picking up my pen or pencil, and continue on going up at a 45-degree angle. So, the limit exists, but it's not equal to -1. So p of 0 exists, the limit of p of x exists, but they're not equal to each other. So in this theorem, we're going to give a few different ways of thinking about continuity. In fact, we can even think of these as alternative definitions, but only in the case that x naught is an accumulation point of D. Okay. So this is a very particular situation. In this particular situation, we can offer essentially alternative definitions of f is continuous at x naught. And again, what do I mean when I say that these conditions are equivalent? If one is true, they're all true. And if one is not true, none of them can be true. And we're going to prove it by essentially making a round. We're going to show 3 implies 2, 2 implies 1, and 1 implies 3. By showing that circular implication, we prove that they're equivalent. In other words, if 1 is true, it implies all the others. And if 1 is not true, then none of them can be true. So let's start this chain of logic off. Suppose 3 is true, right? Suppose that for every sequence xn converging to x naught, where every member of the sequence is an element in the domain, that if that's true, then the sequence f of xn converges to f of x naught. So let's suppose that that's true. Now, we also know by hypothesis that x naught is an accumulation point of D. Then there exists a sequence xn converging to x naught, but with no entry equal to x naught. Right? Such a sequence exists. Now, how do I know such a sequence exists? That just because x naught is an accumulation point of a set, that there's a sequence converging to it in the set, but with no entry equal to it. How do I know such a thing exists? Well, Theorem 1.17 of the class textbook proves that such a thing exists, and you also prove something very similar in your homework. Now, if we suppose that statement 3 is true, then the sequence f of xn, right, specifically f applied to this sequence, converges to f of x naught. Then the second statement of the theorem that connects limits of functions and sequences is true. You remember that one, don't you? Let's use our special snap technology to snap back to it. So that theorem said, let x naught be an accumulation point of D, which is a subset of the real line, then the following statements are equivalent. In other words, each implies the other. Let's start with statement 2. If xn is a sequence of elements in D, none equal to x naught but convergent to x naught, then the sequence f of xn converges. If that is true, then the function f of x has a limit at x naught. Okay, so back to where we were. So, we've proven that if 3 is true, then there exists a sequence in the domain converging to x naught but never equal to x naught. That implies that the sequence f of xn converges to f of x naught. So because the second statement of the theorem is true, the first statement is true. The limit as x approaches x naught of f of x exists, and furthermore it's equal to f of x naught. So statement 3 implies statement 2. Now suppose that statement 2 is true, specifically that the limit as x approaches x naught of f of x is true, and furthermore the limit is f evaluated at x naught. So, by definition of this limit existing, we're guaranteed that for any epsilon greater than 0, there's a real delta for which the following is true. If x is in the domain and x minus x naught is greater than 0 in absolute value but less than delta, then f of x minus f of x naught in absolute value is less than epsilon. Now that's almost the definition of continuity. Remember, we noticed that continuity is very much like a limit, except the limit L got replaced by f of x naught. However, we need to remove this, right? Now, of course, we know that an absolute value is greater than or equal to 0 just by the definition of an absolute value. And, well, the less than is satisfied. I need to show the equal part. But of course, as I mentioned, the equal part is trivial. If x equals x naught, then x minus x naught is equal to 0, which is surely less than delta. And if that's true, f of x minus f of x naught is equal to 0, which is, of course, less than epsilon. So we've satisfied the less than, we've satisfied the equal than, which means we've satisfied this condition. And therefore we've shown that f satisfies the definition of continuity at x0. Therefore statement 2 implies statement 1. Now suppose that statement 1 is true. F is continuous at x0. Meaning, for any epsilon greater than 0, there's a real delta for which the following is true. If x is in the domain, and x minus x0 is less than delta, an absolute value, then f of x minus f of x0 is less than epsilon, an absolute value. Now suppose that the limit of xn equals x0. And every element of my sequence is in my domain. Now, again, statement 3 means that if this is true, then the sequence f of x0 must converge to f of x0. But let's suppose that this is true. Well, what does that literally mean? It means that there exists an n, and if little n is greater than this big natural number n, then the difference between xn minus x0 is less than delta. Well, for these same values, because this is true, I've satisfied this condition, meaning this condition is satisfied for the values xn. Therefore, this is true, again for n greater than big N. Well, that's precisely the definition of convergence of this sequence. Therefore, if statement 1 is true, statement 3 is true. And that proves our result. That's all for today.